The very act of trying to measure your position prevents me from measuring your position. And it doesn't have jack shit to do with your consciousness or your mind or your eyes or anything. It has to do with the fact that to know you're there, some information has to come from you to me, like shining a light on you. And the smaller you are, the more susceptible you are to the energy of the light changing your position in space. A quarter spills out of your pants pocket on the back seat of a car and is there in the wedge between the bottom and the back seat. Mm-hmm. And so you try to reach in to get it. And the act of reaching for the coin makes the coin move farther away from you. That's not your mind making that happen. It's the act of the measurement that is affecting what it is you're trying to measure. And this was discovered in quantum physics, and to the point where it's the Heisenberg uncertainty principle. It's one of the basic foundations of all of quantum physics.
The Heisenberg Principle, formerly known as the Heisenberg uncertainty principle, is a cornerstone concept in quantum mechanics that has sparked profound debates and explorations into the nature of reality. Named after the brilliant German physicist Werner Heisenberg, this principle was established in the early 20th century and has since become closely associated with the enigmatic world of quantum physics. It fundamentally restricts our ability to simultaneously and precisely determine certain properties of subatomic particles, such as their position and momentum. Imagine, for a moment, trying to measure both the position and momentum of a tiny particle like an electron. The Heisenberg principle tells us that the more accurately we pinpoint the particle's position, the less precisely we can gauge its momentum, and conversely, the more we try to ascertain its momentum, the less clear its position becomes. This limitation is not due to the limitations of our measuring instruments but is a fundamental aspect of the quantum world itself. This principle challenged established classical physics, where determinism reigned supreme, suggesting that with enough information, we could predict the future states of particles with certainty. The Heisenberg principle, in essence, unveiled a universe where our best hope was to predict outcomes in terms of probabilities and likelihoods, rather than with certainty. It marked a profound shift in our understanding of the universe, particularly when we delve into the microscopic world of subatomic particles. In its early days, the Heisenberg principle faced skepticism and controversy. Physicists who were deeply rooted in the deterministic worldview of classical physics found this notion of fundamental limits on knowledge unsettling. Niels Bohr, a key figure in the development of quantum mechanics, welcomed the uncertainty principle as a fundamental part of the new theory. He saw it as intrinsic to the nature of the quantum realm and famously remarked, "Anyone who is not shocked by quantum theory has not understood it." However, critics like Albert Einstein and Erwin Schrödinger remained skeptical. Einstein, in particular, was uneasy with the idea that the universe might be fundamentally unpredictable. He famously stated, "God does not play dice with the universe," expressing his belief in a deterministic, predictable cosmos. Despite the early disputes, experimental evidence continued to support the Heisenberg principle, reinforcing its position in the realm of quantum theory. The famous double-slit experiment, where particles exhibited both wave-like and particle-like behaviors, further confirmed the probabilistic nature of quantum mechanics. The Heisenberg principle holds great significance in the realm of quantum physics. However, it has been subject to challenges and alternative interpretations. Bohmian mechanics, named after physicist David Bohm, is one of these alternatives. It suggests that particles have definite positions and trajectories, in contrast to the probabilistic nature implied by the Heisenberg principle. Bohmian mechanics challenges the uncertainty principle by proposing that particles can have both precise positions and momenta simultaneously. While this interpretation remains controversial and isn't universally accepted, it highlights that there are alternative perspectives on quantum phenomena that question the central role of the Heisenberg principle. Another challenge to the Heisenberg principle comes from the concept of quantum non-locality and Bell's theorem. Quantum non-locality refers to the peculiar phenomenon where entangled particles, such as two electrons, can instantly influence each other's states, regardless of the physical distance separating them. This concept raises questions about the completeness of quantum mechanics and whether our understanding of quantum reality is as comprehensive as we believe. Let's take a closer look at Bell's theorem, which was introduced by physicist John Bell in the 1960s. This theorem provides a powerful method for testing the validity of local realism, a concept that suggests physical processes are influenced only by their immediate surroundings. Bell's theorem, in essence, proposes that if quantum mechanics is an accurate description of reality, certain statistical relationships between measurements on entangled particles should surpass the limits imposed by local realism. Remarkably, subsequent experiments have consistently validated Bell's inequalities, offering substantial evidence that quantum mechanics indeed allows for non-local effects. This revelation raises profound questions about the classical notion of a locally real universe, to which the Heisenberg principle is intrinsically linked. The challenges presented by Bell's theorem and quantum entanglement suggest that the quantum realm operates in a manner that transcends the constraints of classical, locally real physics, thus leading to a re-evaluation of our understanding of reality in the quantum domain. Let's delve a bit deeper into the Einstein-Podolsky-Rosen (EPR) paradox introduced in 1935, which adds an intriguing layer of complexity to the challenges presented by the Heisenberg principle. This paradox directs our attention to the concept of hidden variables within the realm of quantum mechanics. These hidden variables are hypothetical parameters that, in theory, could predict the outcomes of quantum experiments with unwavering certainty. The EPR paradox posits that the uncertainty introduced by the Heisenberg principle is a consequence of our incomplete understanding of these hidden variables. If we were able to fully account for these concealed parameters, the inherent uncertainty would vanish, and particle behavior could be anticipated with absolute certainty. This challenge to the probabilistic nature of quantum mechanics provokes us to contemplate whether hidden variables might indeed play a fundamental role in governing the behavior of particles. Beyond the theoretical challenges to the Heisenberg principle, experimental investigations have sought to test the validity of quantum realism. These experiments take various approaches, including the violation of Bell's inequalities, the search for hidden variables, and the exploration of alternative explanations for quantum phenomena. These challenges to the Heisenberg principle do not negate its practical utility within the domain of quantum physics. The principle continues to be an essential tool for understanding and predicting particle behavior. However, it's crucial to acknowledge that these challenges carry profound philosophical implications, serving as a constant source of inspiration for further exploration of the mysteries inherent in the quantum world. The Heisenberg principle and the challenges it raises regarding alternative interpretations and experimental tests compel us to dive deeper into the concept of local reality within the universe. This exploration fundamentally challenges our classical intuitions about how the world operates, offering a stark contrast between the quantum and classical realms. In the quantum world, traditional ideas of determinism, locality, and predictability are upended, prompting us to re-evaluate our understanding of the nature of reality itself. Thank you for watching another episode of Space Odyssey. While you are still here, don't forget to like and subscribe.